Hi, my name is Anjali and welcome back. Today we are diving into an interesting topic in algorithm, the fast and slow pointer technique. This technique can be super handy, especially when it comes to finding the midpoint of the linked list. So without wasting any time, let's get started. We will first understand the problem statement correctly and then we will jump to different solutions. Imagine a linked list 1, 2, 3, 4, 5, 6, 7, 8, and 9. Our goal is to return the value at the midpoint, which is 5. You can clearly see the value at the midpoint is 5 and we need to return that. Now, as we understood the question, we will look at the different solution to the specific problem. One simple approach to find solution to this problem is to return the value at the length by 2. But this is a linked list and we don't know what length it is. So it requires us to traverse the entire list to find its length, which is 9 in this specific case, and then traverse again to reach the midpoint, which is still 9 by 2. As it is requiring us to traverse a list twice, this approach is simple but bit lengthy approach. We need to optimize our solution. So the question comes, can we do better? The answer to this question is yes, we can do better by using fast and slow pointer technique. Let's again understand with an help of example because that's the best way to understand it. Taking the previous linked list shown above, 1, 2, 3, 4, 5, 6, 7, 8, and 9, where our goal is to return at the value at the midpoint, which is 5 in this case, we will be applying fast and slow pointer technique. So we'll be having two pointer, slow and fast, initially pointing towards the head of the linked list and moving at different speed within the linked list. As the name suggests, slow will be moving slowly and the fast will be moving fast. How it will navigate, we will see. Slow pointer will move one step at a time, whereas the fast pointer will move two steps at a time. Let's use simple illustration to understand how slow and fast pointer moves in each and every iteration. So here we have our linked list and initially slow and fast pointer are both pointing towards the head of the linked list. And in each iteration, slow is moving one step at a time, whereas fast is moving two steps at a time. Let's see what happens. In the first iteration, slow will move from 1 to 2, whereas the fast will move from 1 to 3. I'm going to write with a different, this is the S1 transition, this is a F1 transition. Also, I'm going to make one table with name as iteration, location of the slow pointer, and the location of the fast pointer. So in the first iteration, slow is pointing towards the second node, whereas the fast is pointing towards the third node. Let us see what happens in the second iteration. In the second iteration, slow is moving from 2 to 3, whereas the fast is moving from 3 to 5. So this is S2 and this is F2. Also, we're gonna entering the table. So in the second iteration, it has moved towards 3 and the fast has moved towards the 5. Let's see what happened in the next iteration. It will move to 4 and it will move to 7. This is S3. This is the third iteration for the fast pointer. In the third iteration, they're pointing towards the 4 and it is pointing towards the 7. In the fourth iteration, slow will move towards the next, which is 5, whereas the fast will move towards the 9. We're going to write this in the table. This is the fourth iteration. This is the fourth iteration. Making this entry here, it has moved towards the fifth fifth node, whereas it has moved towards the ninth node. So what do you see from this table? The observation is we are able to find the midpoint in the slow pointer when our fast pointer is pointing towards the last node. This is quite evident over here. So what is our exit condition? We have to keep going till our fast pointer is pointing towards the last node. What will be the condition here? That fast dot next here becomes equals to none. Let's discuss another example where the length of the linked list is even. So if you have noticed one thing over here, the length of the linked list is odd. And in the previous video, I have clearly mentioned one tip that you need to consider both the scenarios odd and even. We know that this is the condition which is true in case of the odd length, but what about the even? Let us explore with the help of an example. Let's take the below linked list where the length of the linked list is even, which is 10 in this case, and see how slow and fast pointer move across the linked list. So we have the slow pointer and the fast pointer initially pointing towards the head of the node and taking one step at a time, and taking two steps at a time. So the slow will move from 1 to 2 in the first iteration. I will write S1 here, whereas the fast will move from 1 to 3. We will write F1 here. And also we will be making one table as we made in case of the odd scenario: iteration, location of the slow pointer, and the location of the fast pointer. So the first iteration, slow is pointing towards the 2 and the fast is pointing towards the 3. Nothing changes, everything is same as we did in the odd length. But we want to see what condition comes in the end. For the next loop, it will move from here to here. I will write S2. Again, it will move from here to here. So in the second iteration, slow is pointing towards the 3 and the fast is pointing towards the 5. In the next iteration, slow will move from here to here and the fast will go from here to here. Nothing is changing, everything is same. Let's keep going. For the S3, it's 4 and 7. What about the next? It will go from here to here and the fast will jump from 7 to 9, F4. In the fourth iteration, it has moved from 4 to 5 and this has moved to 9. Now, in the fifth iteration, let's see what happened. It moved from this to this. This is S5 and the fast will move from this to this, which is null here. So we'll write it down here. Fifth, we got 6 over here as the slow pointer and we got null in the fast node. Surprising. In the odd length scenario, we got the last node, but in case of the even, we got as null. So here we can see that we got our midpoint, which is 6 in this case, and we need this value, but the condition changed here. We are getting our midpoint within the slow pointer when the fast is equals to null. So the condition, the exit condition of the loop becomes when fast is equals to null. So that's why it's very important to consider both odd and even length so that we can judge what condition is coming in the end. I hope you got the point for the odd and even length. And now we have to combine both the scenarios, both the conditions. Let's see how. Let's write pseudocode from both the conditions of odd and even. So we will write the algorithm like while fast is not equals to null, keep on going, because if fast is equals to null, there is no point in iterating. We have to iterate where fast is not equals to null. And what odd says is that fast dot next should not be equals to null. So these are the two conditions. This is from the even and this is from the odd. Now you have noticed one more thing, that I have written the even first and then I have written the odd because it makes simple sense. If fast is equals to null, then null, if you check for null dot next, it will give you error. So that's why fast is equals to null. It will not check for this condition. That's why it's important to write this condition first and this condition first. So while these conditions are true, keep on going. Slow will become slow dot next and fast will become fast dot next dot next. And simply we can return the slow which contains our midpoint. This is simple as that. If you understood the pseudocode, I want you to make one more observation here. If you see this linked list carefully, you see that there are two midpoints here, 5 and 6. 5 and 6, I'm sorry. They both are considered to be as midpoint when the length of the linked list is even. So what we are saying is when the length of the linked list is even, there are two mid nodes. One is known as the left mid node and the other one is known as the right mid node. Let's see at the table what we got in the last iteration, what the one which we are returning here when fast is equals to null. So when fast equals to null, the slow contains value 6 or the node 6, which is the rightmost midpoint. But what about the thing when we want to find the leftmost midpoint, which is 5 in this case? Let's make some observation in this table and see that we got leftmost midpoint in the second last iteration. This is our midpoint, which is the leftmost, and we are getting in the second last iteration. So how can we return this value if somebody asks for the left mid node instead of the right mid node? To do that, we need to introduce another new variable known as the previous underscore mid. What this previous underscore mid will do is it will act as a keeper. What does mean is meaning it will hold the original value of the slow pointer before any updates. This is very important. For example, what does it mean? Let's look. So our linked list look like 1, 2, 3, 4, and so on. So slow pointer is initially pointing towards the head of the node, and in each iteration it is moving one step at a time. So in the first iteration it has moved from 1 to 2, but initially before changing its value it is pointing towards the first node. So in the first iteration it has slow pointer has changed its value from 1 to 2. So its initial value is 1 and then it has moved to 2. So what it will do is previous underscore mid will act as a keeper, and it will store this value here in the previous underscore mid. We will keep the initial value of the slow pointer in each iteration before changing, before making any updates. So in the second iteration, the slow pointer has changed from 2 to 3, but its initial value is 2. So in previous underscore mid, we will keep the value 2. In each iteration, we'll keep on storing the initial value of the slope. I hope you got the point. So what it is saying is, so before we move the slow pointer, one second, so before we move the slow pointer to the next node, we save its current value in the previous underscore mid. That is what we are doing. In previous underscore mid, we are storing its current value. Current value. Let's make another column here with black pen. So I will make another column here as previous underscore mid. So in the first iteration, initially the value of slow is 1. In the second iteration, the initial value of slow before changing is 2. In the third iteration, its value initially was 3. In the fourth iteration, it's 4. And in the fifth iteration, it was 5. So what you see here that we got 5, which is our leftmost midpoint in the last iteration. When this condition equals to true, when fast is equals to null, we are getting this leftmost midpoint in the previous underscore mid. So by introducing another variable, we are successfully able to solve leftmost midpoint in the last iteration. Let's make our changes in the pseudocode to accommodate previous underscore mid variable. So we need to define one more variable, that is previous underscore mid, which is initially pointing towards null, and in each iteration it's storing the initial value of the slow pointer. So this here, and in the end, instead of returning mid, what we need to return? Previous underscore mid, which contains the value for the leftmost left midpoint. Let's recap before jumping to LeetCode problem. What we have learned so far: for finding midpoints, we have two scenarios. For odd, we have to iterate till fast dot next not equals to null. For even, we have to iterate till fast is not equals to null. But we have two midpoints in case of even, left and right. For left, we need to introduce another variable like previous underscore mid to store original value of the slow pointer. For right, we just can simply return the slow pointer. I hope you got these points. Let's jump to the LeetCode problem now. It's time to do LeetCode problem. So this is 876 middle of the linked list. We will be implementing what we have learned so far. Let's see the question first. Given the head of a single linked list, return the middle of the linked list. And if there are two middle nodes, return the second middle node. What we know about two nodes, that in case of even, like here, we have two mid nodes 3 and 4, but we need to return the fourth one, which is the rightmost. So we don't need to introduce any other variable like we introduced previous underscore mid. We need to keep it simple and just simply return slow. Let's implement what we have learned. We need to have two pointers. Let's note slow, which is pointing towards the head, and similarly let's node fast, pointing towards the head. What are the conditions? While fast is not equals to null, which is for even, and fast dot next not equals to null, keep on iterating. Our slow will move one step at a time, which is slow dot next, and fast is fast dot next, which is two steps at a time. And we need to return slow, which contains our midpoint. Let's run this program. Fast dot, oh, I'm sorry, this is while. Let's run again. Okay, so both the cases are submitted. Let's try to submit it. This is what we get after submission. Our runtime is 100%. That this is our memory use. It means our code is optimal, and we have written the optimized solution by using slow and fast pointer. I recommend you to write this program by yourself from the understanding what you got from the pseudocode. Now it's time to have a cup of coffee and test the knowledge and work on follow-up question. The question here is that you need to delete the middle node of a linked list. For example, here the linked list is 1, 3, 4, 7, 1, 2, and 6. You need to delete the middle node and return the modified head. So the output would be 1, 3, 4, 1, 2, 6. When the length of the linked list is even, you need to delete the rightmost midpoint and return the modified head. So here the length of linked list is 4, so you need to delete the rightmost midpoint over here. So the output would be 1, 2, and 4. I hope you got the question, and the link for this question is given in the description below. Please go ahead and solve this question by yourself, and if you face any difficulty, we will solve this question in follow-up video. I hope you have enjoyed this video very much. Notes are available in the description below. Please do like, share, and subscribe. We'll meet in another video. Till then, bye bye. Take care.